This question is about 1-chloropropane. Define the term standard enthalpy of formation. So all the enthalpy change definitions all start with the enthalpy change when 1 mole. So the enthalpy change, you could change that to the heat energy change, but it would have to be heat energy change. So the enthalpy change when 1 mole. Now we're doing formation here, so of a compound or a substance is formed from its elements all substances in their standard states. The equation for the reaction used to manufacture 1-chloropropane is shown. The enthalpy change for this reaction is minus 114 kilojoules per mole. And then we've got some enthalpy of formation data, and we're being asked to calculate the enthalpy of formation for propan-1-ol. Bearing in mind that propan-1-ol is here in our equation, using the enthalpy change data in the table and the enthalpy change they've given us. Now, because this is formation data, it's about forming things from the elements in their standard states. So we could create a cycle and if I just put these state symbols on, from the elements, so we have got carbon, which is a solid, 1, 2, 3 carbons on each, not actually 3, 9 carbons on each side, because 3 propan-1-ols. And then we've got 3, 4, 5, 6, 7, 8 times 3, 24 hydrogens, or 12 H2 gas, a phosphorus. So we can just put P. We could have put a quarter of a P4, but P will do for this, and then 3/2 Cl2s, and we're forming these substances at the top from the elements in their standard states. So we know that the top arrow is minus 114. Here we're forming 3 propan-1-ols, but we don't know the value, and a PCl3, and here we're forming 3 1-chloropropanes and a H3PO3. So we can add up this side, minus 130 times 3, minus 972. And we're getting minus 1362. And this side we've got 3x minus 339. And according to Hess's law, enthalpy change is independent of root. So the one we want is inside this left-hand arrow. If we go a different way to get that left-hand arrow, we could say that 3x minus 339 equals minus 1362 minus 114. So 3x equals minus 1362 minus 114, which becomes plus 339. We could type that on our calculator. So 3x equals minus 909, so x equals minus 303. There is another way to do this. You may have learnt that if you're given formation data, that delta H equals the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants, and that would work as well, give you the same answer. 1-chloropropane can also be produced by the reaction of propane, C3H8, and chlorine, Cl2, in the presence of UV light. Why is ultraviolet light needed for this reaction to occur? Well, ultraviolet light provides the energy for the initiation step, and that is to break the Cl-Cl bond and form chlorine radicals. And then it wants the propagation steps, but it very specifically wants them to form one chloropropane. So we must show the structural formula of propane and not use molecular formula so that we can show the location of the radical. So our chlorine radical is going to remove a hydrogen from position number 1. So I'm doing 1 on the right here. So I've lost a hydrogen from carbon number 1 and chlorine's picked it up. That propyl radical then, with that radical on carbon number 1, it's going to react with a molecule of chlorine, because propagation steps are radical plus molecule, makes radical plus molecule. And we're going to make 1 chloropropane and Cl radical. It says the CCl bonding 1 chloropropane is polar because carbon and chlorine have different electronegativities. Define the term electronegativity. So electronegativity is the power of an atom to attract the pair of electrons in a covalent bond. It needs to be specifically in a covalent bond. Ammonia reacts with our 1 chloropropane to form propylamine. So propyl chain and then an amine group. Name and outline the mechanism. So let's just start by having a look at the mechanism. So we've got our 1 chloropropane. I'm just going to draw out the functional group carbon here. And here's my ammonia molecule. Now ammonia's got a lone pair, and so it's going to donate its lone pair to the delta plus carbon, and that makes it a nucleophile. And it's going to swap its position for the chlorine, so that makes it nucleophilic substitution. At this point, because ammonia was a neutral molecule, we're going to end up with a charged nitrogen because it gave away electrons and became positively charged. And so in the intermediate step, we're going to have to deprotonate it. You could show this using another ammonia, but you don't need to, because that is an acid-base reaction that just also happens because of the excess ammonia in the beaker. I'm just going to show it losing its proton.